Hello, everybody. We continue to study sufficient condition for differentiability. Let me recall Theorem 3, which was formulated during last lecture, says if partial derivatives with respect to every variable are continuous, at a point x naught I from 1 up to n, then f is differentiable. At x naught. That is what was formulated last time. And now the proof. So we want to prove differentiability. Let me recall what it means the function is differentiable. We need to consider the increment of the function. That is, now let me write it in details. So I take every coordinate of the point x naught and add some increment to that variable. And let me recall also that here I suppose that we have vector of increments delta x1 on delta xn, and the vector x naught is also given by its coordinates like that. So that is the increment, and we need to prove that this is equal to special expression. I'll recall it a little bit later. Just now I want to transform this difference. So how we'll do it? So you see, we have a difference when each variable changes. But I want to split the difference into several differences in such a way that for each time only one variable varies. Other variables are constant. So how we can do it? So we started from the same point as at the beginning, and as I said, I want to change only one variable. So let me start to change the last variable, nth variable. So I subtract x1 naught plus delta x1, so on. So all variables except for the very last are the same as before, but the very last will be different without this delta xn. Of course, this value doesn't appear from the beginning, so I need to compensate it. So I compensate this value And now I'll change the variable with number n minus 1. So it means I don't want now to write down the variable n minus 2. So it will be written like that. So you see, the variable with number n minus 2 is the same as here. But the variable with number n minus 1 is different from that one. Its variable is the same. Of course, we need to compensate it, and so on. We continue this up to the very last step, where we compensate the value when only the first variable is different from x naught. And of course, lastly, we have our value at x naught. So you see that I added and compensated this addition, better to say I subtracted and compensated several values of the function f. Now what we do? We look, for example, on the first difference. So I can split now the total sum into n differences. For each differences, considerations are similar. So I'll do it in details for the very first. So what we have here? All variables except for the very last are fixed. Hence, we have a difference of the function of one variable. This function, I don't want to introduce new notation. So this is similar to phi n minus 1, which was considered last time, but now it's slightly different because of, see, here also variables are different. And how we can denote it? Yeah, for example, let's say psi. So I'll denote here as psi n minus 1 of x n naught, psi n, x n naught plus delta x n minus psi n at x n naught plus so on. As I said, all other differences will be considered analogously. So what is psi n here? Psi n is the function of one variable xn, and it is determined as f with other values which are the same as both here. You see, all other variables are the same as are values here in this first difference. The last variable varies. That is xn without any extra index. So then what we see here? We have a difference of values of a function of one variable at two different points, and if delta xn is sufficiently small, then the function psi n is differentiable as a function of one variable. Why? Because f has partial derivative with respect to xn, I equals to n. So let me write it here. df over dxn exists in the neighborhood of x naught. Hence, psi n is differentiable at x and naught. So only as a function of one variable, because all other variables are fixed inside that neighborhood. So the function is of one variable is differentiable. Hence, we can apply Lagrange mean value theorem. Lagrange mean value. And then what we obtain? There exists a point between, let me denote that point psi n, times difference of values of x n. So psi n is somewhere between, psi n is between x and naught and x and naught plus delta xn. So in a picture, let me do it for two variables. So we have a point x naught here, right? We consider second variable. So it means somewhere here is, that is delta x1, that is delta x2. So we start, so here we have x naught plus delta x vector. Both variables got some increments. Now what we do? We fix this delta x1. So it means we consider a function of one variable x2 only at those 2 points. Other coordinates are fixed with increments delta x1, so on, delta xn minus 1. So psi n is, in fact, psi n only second coordinate. So other coordinates are as before. So let me omit for a while other terms of this sum. So what is psi n prime? Psi n prime, as we see by definition, is partial derivative of f with respect to nth variable. So I can write df over dxn. Now at which point? All variables here, except for the very last, are written. So let me rewrite them here, like that. And the very last variable, here we applied Lagrange mean value theorem, so some psi n appeared, and we have psi n here. And times the difference is equal to delta xn. So that is how we proceed with the very first term of our sum. So here on the picture, what is this point? This point has two coordinates, x naught first coordinate, x1 of first coordinate of the point x naught plus delta x1, and the second coordinate is psi1. So here n equals to 2. So the point is intermediate point for the Lagrange mean value theorem, but Lagrange mean value theorem works only for the second coordinate on the picture, n equals to 2. In general, we have many variables, so nth variable. And we can proceed for each term of our sum analogously. So what we obtain here, for example. So second term will be partial derivative of f with respect to x n minus 1 at a point now, which point? So all variables up to n minus 2 are the same as before. So let me write once xn minus 2 naught plus delta x n minus 2. Then the variable n minus 1, we applied Lagrange mean value theorem. So we have some intermediate value psi n minus 1. Then the last variable here, x n naught, times delta x n minus 1. And so on, analogously up to the very last difference. Here we apply Lagrange mean value theorem to the first variable, to the first coordinate. So we have partial derivative with respect to x1 at a point psi1, and then x2 naught, so on, xn naught times delta x1. That is how we transform our difference. Now, recall that we want to prove the differentiability. It means that I have to transform, I have to prove that this difference can be represented as scalar product of gradient times delta x, and scalar product of gradient times delta x is equal to partial derivative of f with respect to x1 at a point x naught times delta x1 plus so on plus other coordinates. But you see, so I want to obtain this term, but I haven't it. I have a different. Here I have some psi1. So let me now write in inverse order. So I start with the very last term. So here what I have psi1. I want to obtain that one. So let me compensate this, and it gives df over dx1 psi1 x2 naught, so on, xn naught minus that one compensation at x1 naught, x2 naught, so on, xn naught times delta x1. So you see, I transformed the very last term of our sum into the sum of those two terms. And analogously, we proceed with others. And let me omit all others except for the very last, which is obtained from the first. So, what is it? Let me write it here. Partial derivative of f with respect to xn at x naught times delta xn. Once again, that is what I want to obtain because of differentiability. which I want to prove. And then we need to compensate this, because we had quite a different expression. So that is partial derivative of f with respect to xn at a point x1 naught plus delta x1, so on, up to xn minus 1 naught plus delta xn minus 1 psi n minus partial derivative of f with respect to xn. Once again, let me write in coordinates, like here. X naught, I prefer to write in coordinates here. Yeah. That is how we transformed our difference. Now, I want to prove that this is equal, that is the claim, in fact, the claim that it is equal to differential, which is, that is, this sum is differential. That is differential f. Right. Plus little o of delta x, as delta x tends to 0. That is what we want to prove. What we want to prove. Okay. Now, so it means that I want to prove that all those compensated terms are little o of delta x. So, to prove that claim, it is sufficient to check that the limit as delta x tends to 0 vector of, let's say, let me consider in details the last term, x1 naught plus delta x1, so on, xn minus 1 naught plus delta xn minus 1 xi n minus partial derivative at x1 naught, so on, xn naught times delta xn over delta x vector length. So that should be equal to 0. That is what I want to prove. So to prove the differentiability is by definition this equality. Hence, if we look at those two expressions, we see that we need to prove that each of extra terms, those compensated extra terms, is little o of delta x. And it is equivalent to prove that that is 0. That limit is 0. Okay. But look, delta xn over length of delta x, what is it? That is delta xn over square root of the sum of squares of coordinates, length of vector in Rn. So modulus of this expression less or equal to what? I can obtain an estimate above if I'll replace every term in the denominator by 0 except for the very last. So then we have delta xn divided by square root of delta xn squared, and that is 1. So you see, this term is bounded, less or equal to 1. And what is for the difference in brackets? You see, here we have the value of our partial derivative with respect to xn at the point x0. What is about that one? That is the value of the same partial derivative at another point, but you see, psi n is between, вы следите за мной? Psi n is between xn naught and xn naught plus delta xn. Hence, that point, you see, that point. So for the picture, it's here, right? It's here. If delta x tends to 0, delta x tends to 0. So it means that distance tends to 0. And distance from our point to x0 is strictly less than delta x. So the length of the difference between point x1 naught plus delta x1, so on, xn minus 1 naught plus delta xn minus 1, psi n, and x1 x naught, that distance is less or equal than delta x, the length of delta x. Hence, it tends to 0, as delta x tends to 0. So we have the term in brackets is infinitely small, tends to 0, and other multiplier is bounded. And product of infinitely small times bounded is infinitely small. So we have 0 here. And it means that theorem is proved. Theorem is proved. That is very important proof, in fact, and of course you should know it. Okay. Next theorem is theorem 4, multivariate chain rule. So if f is differentiable at y naught equals to y1 naught, so on, ym naught in Rm, and functions yj's are equal to gj of x are differentiable at x naught in Rn for all j, and also let me write yj naught equals to gj of x naught. So everything what is written with index j is valid for all j from 1 up to m. Then the composition h f of j is differentiable at x naught and gradient of h at x naught can be represented as gradient of f at x naught times the matrix which is formed by gradient of gj's. So, oh, sorry, here y naught, x naught, so on, gradient gm at x naught. That is matrix. It is matrix m times n. And so here we have vector or matrix 1 times m, and here we have vector or matrix 1 times n. So according to matrix multiplication, we have this possibility to multiply matrices. And let me write also in coordinates. This equality is so dh over dxi, let's say, at x naught equals to the sum j from 1 up to m df over dy I at y naught times j index is j over dxi at x naught. I from 1 up to m. So how to remember it? Because definitely it looks rather complicated. But let me write more practical thing to understand what is going on. So what we have? We have a function of n variable h, which is represented as f of g1 of x1, so on, xn, and so on, gm at x1, so on, xn. Now, and that is y1, that is ym. So recall for one variable. So what happened for one variable? We had h of x, f of g of x. And how we proceed to find the derivative? H prime of x was equal to f prime at g of x times g prime of x. That is chain rule for one variable. Now look what happens for several variables. So for one variable, we took derivative of, firstly, of outer function, and then multiply by the derivative of inner function. But now you see, we have one outer function, but we have many inner functions. So it means that what we have to do, we proceed like for one variable. So each term here in the sum is like it was for one variable. So we differentiate f outer function with respect to inner variable y1, df over dy1, and multiply by the derivative of the same function, which is here, right? And we differentiate that function with respect to that variable which we want. So you see, xi is the same as here, xi. So, in other words, each variable x1 up to xn, you can find it at every place, either inside y1 or inside ym, and for all of them between. So if we want to find the derivative with respect to one of those variables, we look where we see that variable, and we differentiate f with respect to each place where we see it, and then we differentiate that place. And then we add together the results. That is how to proceed it in practice. And of course, the matrix form is also very convenient, because here, if you think that you replace in general, so for several variables, gradient is replacement of derivative. So instead of derivative f prime, we have gradient of f. Instead of derivative of g prime, we have many functions g. So we have matrix which consists of gradients. So this rule is generalized in that way. So now derivative is vector of matrix 1 times m, and g prime is matrix m times n. In fact, also it has such a meaning in rigorous sense, but I don't want to do it in this course. Okay, now proof of that theorem. And the proof is essentially easier than to understand the formulation, in fact. So, we want to find partial derivative with respect to x. Let me do it for one variable, let's say x1 at x0, right? Sorry. Firstly, we need to prove the differentiability, right? So we need to consider, that is, we'll obtain it automatically, in fact. So I need to consider the increment of our function h. It seems I have to stop, right? But let me write that increment, and then, so that is a x1 naught plus delta x1, so on, x n naught plus delta xn minus h x1 naught, so on, xn naught, right? And now what is it? That is f of g1 of the same list of variables, so on gm of the same list of variables, right? Yeah. Minus f g1 x1 not so on x and not so on gm x1 not so on x and not. Okay, that is the difference which we need to consider. Okay, let's have a break. The difference between the related coordinates, okay, like that, for f so you see what I consider here. I consider here the difference between corresponding coordinates in the list of the argument of the function f. So let me denote it by y delta yj, delta yj, j from 1 up to m. So with the help of this notation, I can rewrite the difference as f of g1 x naught plus delta y1 so on gm at x naught plus delta ym minus f at okay, let me write like that firstly. But remember that those ji's at x naught are yi's. So we have precisely the increment of the function f at the point y naught. And f is differentiable, hence we can write it down as scalar product of gradient of f and y naught times the vector delta y plus little o of delta y, of the length of delta y, as delta y tends to 0. Okay, let me write down in details what is this scalar product. So that is sum j from 1 up to m, partial derivative of f with respect to yj's at y naught times delta yj. Delta yj is written here, so I substitute this expression. Yeah, that is delta yj is written here, plus little o of delta y I rewrite. But now what is written here is precisely, that is precisely the increment of the function gj. And functions gj's are differentiable. Hence, once again, we can apply the definition of differentiability. So I will rewrite it as j from 1 up to m, partial derivative f with respect to yj at y naught, right? And then sum I from 1 up to n, okay, bracket, partial derivative of gj with respect to xi at the point x naught times delta xi plus little o of delta x. But since I have I have m functions gj's, hence little o are different, so let me indicate it by index j here. Yeah. Plus little o of delta y. And so the question is, if this is equal to, so that is our question. And in fact, if I change the order of summation here, then I can write like that: I from 1 up to n, then sum j from 1 up to m, partial derivative f with respect to yj at y naught times partial derivative of gj with respect to xi at x naught, yeah, times delta xi. So I changed the order of summation, and delta xi is a common multiplier for each of those terms, right? And to prove that function h is differentiable, what we need? I started with the increment of the function h. So I need to prove that everything else, what rest, is little o of delta x as delta x tends to 0. So that is our question. That is our question. And yeah, because if we will prove it, then everything is proved, since automatically we obtain also this expression for partial derivative as a consequence. Because look, here is the coefficient in delta xi, that is precisely that expression which we want to prove. So it means that that is equivalent to prove this equality. It's equivalent to prove that everything except to this product of two sums is little o of delta x. So let me write it in details. Sum j from 1 up to m, partial derivative of f with respect to yj's at y naught times little oj of delta x plus little o of delta y is little o of delta x as delta x tends to 0. That is what we need to prove. So how to prove that something is little o of delta x? We need to divide it by delta x. So we need to check what is about limit as delta x tends to 0 of this expression, sum j from 1 up to m, partial derivatives yj at y naught times little oj delta x over delta x plus little o of delta y over, yeah, I'll write like that for a while. And then I'll insert something. So this should be 0. That is what we want to prove. And look, this term, each of those terms tends to 0 by the definition of little o. So we have finitely many terms, each of them tends to 0, so this sum tends to 0. But here it is not clear, firstly, but we can insert such an expression. Of course, we need to distinguish here between the cases if delta y is 0 and not 0. If delta y is precisely 0, then of course I cannot do it. But what happens if delta y is precisely 0? Then we have precisely 0 here, and it means that in this case our increment is precisely 0, so nothing to prove if delta y is identically 0. So I can suppose delta y is not identically 0. And in that case, you see, this tends to 0 as delta y tends to 0. That is a little bit different from what we want, because we want to have delta x tends to 0. But look at this ratio. So what we need to do, we need to consider in details this ratio. Delta y over delta x. So that is, let me write like that. Square root of delta y is a vector of those increments, delta yj's. So let me write each of them in details. Yeah, in fact, just one of them I'll write in details, like that. Square root. So g1 x naught plus delta x minus g1 at x naught squared over here delta x squared. I'll insert it into under the square root plus so on, and I'll do in the same way for each of increments. Squared. And then you see that for each of jj's, look, we can write as follows. Over delta x is equal to, remember, functions gj's are differentiable, so I can write sum I from 1 up to n partial derivatives with respect to xi times delta xi plus little o of delta x over delta x. Delta xi over delta x in modulus is less or equal to 1. We did it today. So it's analogously, we divide one component by the length of the whole vector. So you see, that is bounded, right? And we have finitely many terms, bounded expression times some number. So this quantity is bounded, and the rest tends to 0. So it means altogether we have here bounded. And what it means bounded? It means modulo delta y less or equal than some constant times delta x. And if delta x tends to 0, then delta y is also tends to 0. So it means that from this inequality we obtain that once delta x tends to 0, delta y also tends to 0. Hence, indeed, the last term tends to 0 as well. And now theorem is proved. Okay, that's it. Yeah, and as a corollary, yeah, but before to write down the corollary, let me make an agreement like for one variable, like for the case of one variable, we denote delta x I equals to dxi, I from 1 to up to the n, if x1 so on xn are independent variables. That is an agreement which was made for one variable. Now I'll do the same for several variables. And then differential of the function f, if it is differentiable, can be written as sum I from 1 up to n partial derivative times dxi. So that is the standard formula for the first differential. So now let me formulate the corollary. The formula for the first differential df equals to, okay, let me write here points. Partial derivative with respect to xi at x naught times dxi is valid not only for the case of independent variables, xi's, but also in the general case. That is called maybe like that. Let me write i.e. the first differential has invariant form. This property was valid for functions of one variable, and now you see it is valid for functions of several variables as well. So, proof. So now we want to understand what happens. So if xi's are let me very bad idea was here. Okay, I'm sorry, but now it will be different indices everywhere. Gi of y vector, I from 1 up to n. Yeah, that was, I should change here. Okay, let it be like that. If xi are functions, then f of x is a function h of y, which is written in detail as f of g1 of y, so on, gn of y. So you see, comparing with theorem, I changed roles, y's and x's. It's a bad idea, of course. Okay. And then by theorem 4, which we proved just now, we can write differential h, which is at y naught, let's say. What is y naught? Of course, x naught is g, x j naught is gj of y naught, j from 1 up to n. Yeah. So differential, by the definition of differential, can be written as j from 1 up to m partial derivative of h with respect to y j's at y naught times dyj. But by theorem 4, we know those partial derivatives can be written as, okay, here I should change the sense of each of indices. So now I from 1 up to n, I differentiate. So the function h is f of j, so that is the only thing which is the same. df over d xi at x naught times dji over dyj at y naught. I changed roles of x and y's. That is not good, of course, but so I substituted partial derivatives, right? These are partial derivatives. And yeah, let me preserve dyj's for a while. And then if I'll change the order of summation, we have sum I from 1 up to n partial derivative of f with respect to xi's. at x naught. And then what we have, so in brackets, let me write firstly like that, j from 1 up to m partial derivative of gi with respect to yj at y naught times dyj. But what we have in brackets, that is precisely differential of the function gi, or gi is precisely, so we replace dxi. So once again, we have the same formula. But now dxi is differential of that function. That's it. Okay. Okay. Now we start new section. Section 2. Section 2. Geometric sense of partial derivatives and gradient. Section 2. Geometric sense of partial derivatives and gradient. Oh, by the way, there was a question about a generalization of L'Hopital rule for several variables. Let me answer this question. Look, so this chain rule shows that the only natural analog of derivative for one variable for several variables will be vector of gradient. So you see, chain rule is generalized completely by this analogy. So you see, analog of derivative is gradient. But in L'Hopital rule, we had that to compute the limit, we replace ratio of two functions by ratio of the derivatives. But as you know, there is no notion of ratio of vectors. Hence, we cannot expect any possibility to generalize L'Hopital rule for several variables. Okay. Now, let me start with definition. So, a domain in Rn is an open connected set. So it means that we can connect arbitrary 2 points by a curve which is in our domain. Okay, now I'll start with partial derivatives, and let me give one more definition. Parametrically given surface in R3 is the set of points x, y, z R3 such that x is, okay, let's say phi of uv, y is psi of uv, z is phi of uv. uv in a domain, in a closure of a domain, in R2. So omega is a domain in R2. So what is parametrically given surface? Let me show the picture. So we have the plane R2 uv. We have here a domain omega. For each point of that domain, we have a map which is realized by 3 functions, and as a result, we obtain something in the space which is called parametrically given surface. A particular case, in particular, the graph of a function z equals to f of x, y is a parametrically given surface. Because here we have u is x, v is y, so it means phi of uv is precisely u, which is x, right? Psi of uv is precisely v, which is y, and phi of uv is f of xy. That is what happens when we want to consider the graph of a function. And now what is about tangent plane? So once again, definition. Tangent plane to a surface at a point m naught, to a surface, let's say S, at a point m naught in S, is the limit position of planes which contain three points m naught, m1, m2 of S when m1, m2 tend to M naught. So that definition is quite analogous to the definition of the tangent line, or the tangent line. And in fact, for me it is more convenient to make an equivalent definition. I will not prove the equivalence. Equivalently, normal vector of or to the tangent plane, is orthogonal to the limit position of an arbitrary chord of the space of the surface S through two points M naught, M1 of S, as M1 tends to M naught. That is equivalent. In fact, the equivalence is almost obvious, but nevertheless I have no time to prove it. And it seems I have no time to prove the geometric sense of partial derivatives even. So what I want to prove, that in fact okay, maybe once again like before, to formulate theorem and to make the proof often, but I don't want to do it once again. So maybe just I'll make a picture. So you see we have a point M naught, right? So two ways, either to take points M1, M2 and obtain a plane which goes through those points and then take the limit, and another way, look only at 2 points and follow the normal vector. So in fact, in both ways we will obtain the same plane, which is tangent to our surface. So normal vector is orthogonal to each, okay, let me do it here. It's orthogonal to each limit position of a chord. We know if we consider a chord, then, so if we consider a curve on the surface, then the limit position of such a chord will be tangent to that curve. So it means that tangent plane consists of tangent lines to arbitrary curves on the surface which contain M naught. So if you consider arbitrary curve on the surface, find tangent line, then this tangent line will be a part of tangent plane. So tangent plane consists of all tangent lines to all curves in the surface. That is another point of view how to imagine the tangent plane. Okay, we'll do in detail next time. Thanks for your attention.